Hi everyone, this is Zhibo. I'm very excited to share with you our work on unifying top-down and bottom-up attention prediction using transformers. In general, human attention comes in two forms, bottom-up and top-down. The bottom-up attention refers to the attention of a person when viewing the image freely. On the contrary, the top-down attention is not only affected by the image content, but also controlled by an external goal of the person. For example, searching for a microwave and a clock in an image will lead to completely different attention maps. For different tasks, the Scanpath can be very different, and we'll often need to choose different models to predict it. In this work, we aim to design a model that can predict both bottom-up and top-down attentions. An important question in Scanpath prediction is how to accumulate information across fixations. Existing methods often use an RNN or a multi-resolution approach, which either sacrifice interpretability or cannot capture spatial and temporal information well. Moreover, existing methods often treat fixation prediction as a classification problem, where they discretize the fixation using coarse grid, which inevitably reduces the prediction accuracy, especially when the input resolution is large. To address these issues, we proposed the Human Attention Transformer, HAT, and treat the prediction of fixation as a dense prediction task. Our model has four modules. First, the feature extraction module uses an encoder and decoder to process the input image into a low-resolution and high-resolution feature maps, approximating our peripheral and foveal understanding of the image. Then the foveation module constructs the foveated working memory by combining the low and high-resolution feature maps according to the fixation history. A transformer encoder is applied to learn the foveation from these tokens. Then we create a set of queries to learn the task-specific information from the foveated working memory using the transformer decoder. Lastly, each learned task-specific query will be convolved with the high-resolution feature maps to produce the fixation heat map as well as a termination probability for each task. To construct the foveated working memory, we first select the low-resolution feature maps and select the high-resolution feature vectors at the fixated locations. Then we add the learnable scale embeddings to each token in order to differentiate the peripheral and the foveal tokens. Lastly, we add a spatial and the temporal positional encodings to enhance both the spatial and temporal information in our tokens. We compare our methods with previous state-of-the-art in target present, target absent search, and previewing settings. This result showed that our methods has the best performance over all the settings and surpassed human oracles in predicting both target absent and previewing Scanpath. The improvement of our method over the previous state-of-the-art is even more prominent when we look at the salience matrix. Here we show the ground truth Scanpath and the predicted Scanpath from different models. In this example, the subject and the models are asked to look for a bottle in the image. You can see that our model not only correctly located the heavily occluded target at the top right corner, but also correctly predicted fixations on the distractors like humans do. In this target absent example where the subject and the models look for a stop sign, our model is the only one that correctly predicted the fixations on both sides of the road, showing a good understanding of the context and the task. In this previewing example, our model also predicted the most similar Scanpath to humans. Here we show the step-by-step predictions and the contribution of the peripheral token of our model. This is a difficult target present search example, where the target laptop is heavily occluded. One can see that the fixation is initially driven by the keyboard on the right, as the laptop and keyboard are closely related objects. After confirming there is no laptop nearby, attention shifts to the left, where the target features start to pop out, and drive the attention to the target and terminate the search. Similarly for the target absent laptop search, the model shows that the keyboard and the table mainly drives the attention. These examples demonstrate that our model can make highly interpretable predictions. So as a summary, in this work, we presented the Human Attention Transformer model, whose prediction is not only accurate, but also interpretable, and our model achieves the best performance in predicting both top-down and bottom-up Scanpath.